Jai Hind friends, I Himanshu welcome you all in this session of programming using assembly language for 8051 microcontroller, and in this program we are going to use interrupts and timers of 8051 microcontroller. We will see that how we can write assembly language code to utilize the capabilities of timers and the interrupts at the same time. So, we are going to start assembly language program to generate a square waveform as we have done earlier in our videos, but in those videos we generated the square waveform using subroutines or called delays. So, here in this program we are not going to use subroutines with our program, we are going to use timers and interrupts capabilities of 8051 microcontroller. So, let me quickly show you the code, or let me open the Keel Microvision and open the project here. I am making new project, and here I am creating a new folder named timer demo, and inside this folder I am making a project timer demo and saving this project. The next thing is required to select the device. So, I am selecting 8089C51 microcontroller. Here it is, and here we can see the specifications of 8051 microcontroller. It is fully static 24 megahertz CMOS controller with 32 IO lines, and 2 timer or counters are available inside it, 6 interrupt sources and 2 priority levels, and UART is also available inside 8051 microcontroller. It is having 4 kilobyte of flash memory and 128 bytes on chip RAM. So, I am selecting this microcontroller. This seems to be good at our end. Now, this is giving me a prompt to copy the startup.a51 to project folder and add files to project. So, I am clicking on no because I do not need such kind of file in our project. Whatever is needed, we are going to write it by ourselves. So, here our project has created as a timer demo project, and target 1 has created with the target device, that is 8089C51 and source group 1. Right clicking on this source group 1 and clicking on the option add new items to group source group 1. Here it is assembly language file, and I am making this assembly language file as main, and I am not giving any extension because by default it is going to have extension .a51. I am adding this file into our target or source group. So, now you can see that inside my source group this main.a51 file has been added successfully. So, this is the space where we are going to write the code for our project. So, let me zoom it a little bit so that we can see, or you can see it better. So, the first line of any assembly language program for the microcontroller is the assembler directive, and that directive is responsible to tell the microcontroller that from which location we want to start our code. So, by default 8051 microcontroller start execution of the code from memory location 0000H. So, we are forced to write the first instruction of our code at memory location 000H. Remember, this is not a choice, this is a compulsory action, because whenever your microcontroller is reset or power up, your program counter value is going to be 0000H. That program counter means that the next instruction is going to be executed from that particular memory location. That program counter means that that next instruction is going to be executed at that memory location. So, if we are not writing our first instruction at this memory location 0, then our program is not going to be executed correctly. So, it is not a choice, it is a compulsory action that we need to write our instruction here. So, the first thing is ORG 0000H. Here I am using hexadecimal number notations, or you can use decimal numbers as well. So, you can write ORG 0. The next instruction that is available, like what is the instruction that we want to use in our 8051, the first instruction of our assembly language code. If we are using the first instruction, we are writing code from the 000H, then we cannot use the interrupts, because remember in last discussion we have discussed about the interrupt vector table. So, interrupt vector table is available from 0 memory location to 23 or 23 plus 8 you can do. So, these much memory locations are basically reserved for using as a interrupt vector address. So, we need to skip these memory location. To skip these memory locations, I am writing my first instruction as ljump ljmp. Let me write my code in a capital letters, so it will be looking good. org 0000h, and here I am writing ljump, that is long jump main. Ljump is a long jump, that means we can jump up to the range of 64 kilobyte. Okay, and that means we can write this main program anywhere is the applicable or is allowable program memory space. Actually, instead we are having only 4 kilobyte of memory available on chip, but in case you have interface some additional memory, then you can go up to the 64 kilobyte of memory. So, this ljump I am writing here ljump main. You can replace this instruction with the sjump or ajump as per your need. And the next thing is, now we want to store our main program. So, I am again directing our assembler by using assembler directive org and space 0050h. I think that I have left enough space for interrupt vector table, or more than the required space. So, it is good. Now, my program is going to be saved start at 0050h, and here I will put the label main. So that whenever, let me fix it, okay, so that whenever this ljump main instruction is being executed and the program control being transferred to memory location 50, and here is going to be our first instruction of our code. So, here we want to generate a square waveform, and at any GPIO port pin, let us say that we are interested in generating square waveform at P2.0. So, first we need to configure the timer. So, remember in timer configuration there were two registers, tmod and tcon. Tmod register was responsible to configure your timer, whether it is a timer and in which mode you want to work with. So, let us decide that we are going to use timer 0, and the mode we have selected is timer mode 1, that is 16-bit timer mode. So, I am loading the TH0 register, move TH0 comma with a value. Let us say this value is FF0FFH. Remember, this is a rule in assembly language programming that if any immediate value of number is starting with alphabet like A to F, then we should write that number with a preceding 0. So, I am following this rule only. So, here I have written I have loaded the TH0 with the value FFH, and again I am loading TL0 with value let us say 0 FAH. So, this is the value FFFA. So, if we want to write this value, so we can say that our timer register is loaded with FFFAH. So, now you can easily understand that if timer is loaded with this value, and when we start the timer, this value is going to be incremented by 1 with every clock's pulse. So, with the next clock pulse, this value will become FB and then FC, then D, E, F, and after reaching FFFF, this value will become 0 because rollover condition, rollover situation is going to be occur. So, let us erase this from here, and now our timer register is loaded successfully. The next thing is we need to define the mode of our timer. So, to mode of our timer, I am using move T mod, and I want to move a certain number in T mod register. That number is going to be, if I am writing this number in binary, let me show you the T mod register. This is the T mod register. So, this is the T mod register. We are working with timer 0. So, here all bits should be 0, 0, 0, 0, 0, and here gate should be 0 because we are going to control our timer with the software control or with the help of instructions or TR0 bit, and this is a timer device. This should also become 0, and we are selecting mode 1, that means 0 and 1 should be here. So, total number becomes 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay. So, I am going to write this thing in our code 0, 0, 0, 0 and 0, 0, 0, 1 B. B signifies here that we are writing this number in binary, and here if we are writing H, that means we are writing this number in hexadecimal number format. So, till now I have successfully loaded the timer register and I have configured our timer 0 in mode 1, that mode 1 is a 16-bit timer mode. The next step, we want to use the interrupts also, and to enable the interrupts I will use the IE register. So, let us quickly see the content of IE register. Here it is the IE register, and inside this IE register we are basically going to use this ET0 because we are dealing with timer 0 only. So, we need to enable this ET0 bit and we need to enable this EA bit also. So, we can do this thing by using different ways. Like one way is if we are not sure about the full register, I can write set bit EA. So, this automatically will set the enable all bit inside the IE register, and if we want to transfer a complete number into the IE register, I will write move IE comma hash. Hash is used for the immediate addressing mode because we are transferring some immediate number here. So, here I can say this should be 1 and this should be 0, this ET2 is 0 because it is not applicable in our application. ES is 0 because we are not setting up, we are not enabling this serial communication interrupt. We are also not enabling this ET1 because timer 1 is not used, we are not using external interrupt 1. So, this is 0, only we are enabling this ET0. So, we will write 1 here and 1 at the place of EA. So, the number becomes 1 0 0 0 0 0 1 0. So, I am going to write this number 1 0 0 0 0 0 1 0 B. Again you can see 1 0 0 0 0 0 1 0. So, this is the number that we are uploading into the IE register of our 8051 microcontroller. So, here I am writing these numbers in binary, but you can also write these numbers into hexadecimal, or you can write this number is this is 8 and this is 2 82H, but I am writing these numbers in binary so that we may understand the concept of bit addressability of these SFRs or special function registers. That is good. So, now our interrupt is enabled and we have successfully loaded the timer registers and we have successfully configured the timer with the T mod register. So, the next step is we want to start our timer. To start our timer, we are writing set bit TR0. Remember, this TR0 is the bit available inside the TCON register. So, this time we have started this timer register set bit TR0. After execution of this instruction, our microcontroller timer is going to be started, and if the value is FFFA, then this value is going to be incremented by 1 after every clock pulse. So, what microcontroller will do at till that time, because we need to provide certain useful instruction to this microcontroller, because this microcontroller is on and it is actively executing the instructions. So, we are creating here indefinite loop, and this is empty indefinite loop. So, to creating empty indefinite loop, I am writing here, and I am making it a label. Let me place it at the right position, and here I am using S jump here. Remember, I have told you earlier that short jumps or unconditional jumps, whether it may be short jump, absolute jump or long jump, all these jumps are basically used for creating the loops, or you can use unconditional or indefinite loops by using these instructions. Or I must say that these are the good implementation of while loop structure in assembly language, as the counterpart is available in the C language. So, here this is the structure of our code org00h L jump main, and we are here into our main code th0 tl0 load has been done, and tmod register has been configured, and IE has been configured perfectly. Good. What will happen when interrupt will occur? Whenever the interrupt will occur, as per the vector table of 8051, this program control is going to be at a specific memory location. Which memory location? Let's remind you. Let me remind you. This is the memory location. So, here you can see that whenever the interrupt for timer 0 will occur, your program control is going to be at 000PH. So, what we are going to do here, I am writing org 000BH. So, I want to store something as a ISR at this particular location, but I am afraid that there might not be good or proper space to store my interrupt service routine, because the space available here is only 8 bits, that is reserved for timer 0 interrupt. So, what I am doing, I am again using L jump instruction, and I am saying that go to this label, and the label is ISR T0, that means interrupt service routine for timer 0, and here at some another memory location, like I am writing org 001 sorry 0100, I am going to save my interrupt service routine for timer 0, right. This is the way how we deal with interrupts and timers, because in the interrupt vector table, the required space or the given space is very low. So, what we do, we leave a address of that particular interrupt service routine at that recommended address. Okay. So, this is similar that if you are going to any house and the person is not available here, and he can leave a letter mentioning the address where you may get that person. So, this is the same scenario that we are going to execute here. So, when the interrupt service routine is going to occur, what we want to do, we are here to generate a square wave form, and for a square wave form, let us say P2.0 should be high for some time and it should be low for some time or for the same time. So, we are basically complementing the status of P2.0 here. So, for complementing CPL P2.0. So, here I have written CPL P2.0. This means that we are complementing the state of P2.0 bit. If earlier this bit was 1, then now this bit will become 0, and if earlier this bit was 0, then now this pin will become 1. So, I have successfully complemented this bit so that we can generate square waveform using the timers. Now we have started our timing calculation from FFFAH. Remember, in the main program we have loaded this timer. When the rollover is going to happen, then the value of TH0 and TL0 are going to become 0000, and if again this timer is started, then next time delay is going to be different, because next time this will count from 0 to FFFFH. So definitely these two delays from FFFA to FFFF and from 0 to FFFF, these two delays are going to be different. So we need to reload the timer registers, and for reloading these timer registers, what I can do, I can copy these two lines from here and paste these two lines here. So again I have loaded the timer registers with the desired value, and let me return from this interrupt service routine. So to return from the interrupt service routine, I can write RETI, right. So this RETI instruction will basically force microcontroller to return from this ISR. In case of subroutine, we generally use instruction RET, but it is a special case, that is interrupt service routine, then we can use, or we should use, the instruction RETI. So I think that my code is completed by now. Let me save this code, and let me build this code. Great. One warning is here, that missing AND statement. Yes, it is right. When my code has completed, then now I need to tell the assembler that there is no code available after this line. So I am using another assembler directive, AND, END. Again save this code and build this code. Now I have got the message 0 errors and 0 warnings. Let us debug this code and see that how these things are working actually. So in order to debug, let me do one more thing. I can go into the target and right click on target 1, options for target 1. Let me select the frequency of this microcontroller is 12 megahertz. Press on OK. Again I will go into the options for target 1, and at the output I am creating this create hex file, so that we can create hex file and we can transfer this hex file into some simulation software, or we can transfer this hex file into the microcontroller IC as well, if we are using right programming tool. So let me click OK and again rebuild this code. This time I have got this message that creating hex file from object timer demo. So my hex file has successfully created. Now we will try to debug this code, and I am clicking on this debug option. This is showing me the evaluation mode warning. It's okay with me, right. And here I am quickly going into the analysis window. In the analysis window, let me set up this first. I am creating new and P2.0, enter. Clicking on this, selecting the display type is bitwise display and color is red, close this. Now this is my analysis window, and I can run this program in burst mode, like a complete program will be executed and you may be able to see the result of this program. So first let us try to run this program, and here you can see that these square waves are generated. You may not be able to see the square waves. Let me zoom out, zoom in a little bit. Now these square waves are visible perfectly, because I have used very small time delay between two occurrences or two complements of P2.0. So the square waveform is like this. Let me stop the execution of this code, and let me again debug this code. So I am closing this debug session, and again I am starting the debug session, so that I can show you the fresh screen, right. So this time I am not going to press this run button, because I am not interested in executing this code in burst mode. but I am interested in seeing that how this assembly language program code is going to execute it. So let me open from peripheral and from timer, let me open the timer 0 window also, so that I can show you what is the situation. So the first instruction executed, I am pressing F11, I have pressed F11. So this L jump ISRT0 has executed, and now the next instruction is going to be executed from their main line, that is move TH0 comma hash 0 FFH. So again I am executing the next instruction. Now you can see that TH0 register has been loaded successfully. Now this TH0 register has become FF. Next instruction execution. Now TL0 has been loaded to FA. Great. And the next instruction is executed, right. So this T mod register has been uploaded successfully, and here you can see now my timer is one mode 1 and 16-bit timer counter mode, and my device is configured as timer, and gate is not cleared and TR0 is not, timer is not on at this particular moment. So the in the next instruction I will see that the status of IE register, if we are interested in IE, so I will go into the interrupt, and here you can see the status of IE register. Now at this moment of time every bit is 0, every bit is 0. So what I am going to do is execute the next instruction. Now you can see that timer 0, this enable bit has been set. Now this bit has become 1. So now my configuration has completed, and now I am going to start the timer. So next instruction, timer has started and TR0 has been set. If there is a click, that means this bit status is 1, and if there is empty space, then this bit status is 0. So I am again executing this instruction. See, from next instruction execution has made the increment in TL0. This increment is based on the machine cycles, because here we cannot count the one clock pulse at a time, but once one instruction execution has taken some time, and in that time this counter has become from FA to FT. Then again I am executing this instruction. Now this has become FF. So if we again try to execute this instruction here as jump here, then my timer is going to be in overflow condition or the rollover condition. So let's try this thing. Now timer overflow has occurred, because now my timer register value has become 0003. What is happening here in my code? Now the program control has been transferred to org000bh, and next instruction that is going to be executed is ljump isrt0. So this is what we are looking for. Next click, and here we are transferred into this new location, that is 100H, and here my interrupt service routine has been stored. Again I am executing this thing. You can see that even we are executing this interrupt service routine written for the timer 0, but here with every instruction execution the value of TL0 is going to be incremented. Like this means that our timer is still on. You can see from here timer is still on and it is still counting. Now our bit has been changed. Now 1 to 0 transition has been occurred, and here again if we are making it, now we have loaded TH0 and next instruction TL0, and we are returning from interrupt. Again we are here as jump here. This is the main instruction where we will remain forever. So this is the situation that is occurring here. Again I am doing this thing, again interrupt has occurred and ISR is occurring. Now you can see by the help of single step execution that how our program control has been transferred between the timers and the interrupts. So if I run this program continuously, then again I will be able to find out this square waveform that we were planning to generate from the 8051 microcontroller using assembly language. So let me close this debug session. That's great. One more thing I would like to show you, that if you want to make a simulation or you want to see that how this thing is going to work on your hardware, I have made a Proteus based simulation here. You can see this simulation. So in this simulation, I have connected one LED with P2.0, and this is the LED connection. You can see from here, right? So this LED is connected with P2.0 and with one series resistance of 330 ohm, and whenever this P2.0 will become 0, this LED will be turned on, and whenever this P2.0 will become 1, then this LED will turn off. And I have also connected one signal analyzer with this P2.0. Let me double click on this microcontroller and select my hex file. So my code was timer demo, and here in the object we have our timer demo.hex file. I am selecting this hex file here. Here you can change the clock frequency if you wish. Let me change it to 12 megahertz and click OK here. Now run this simulation and you may be able to see the square waveform available. Here is the square waveform, and I have told you that the values are very little, so you may not be able to see the difference. Let me quickly change the values, and so that you may be able to see the results. Here instead of FFFA, I am writing 00 and 09. Again here also 00 and 09. Save this code and rebuild that code, because our hex file will be updated in this sense, and again run this program. Now you may be able to see the square waveform generated, and you can see the LED blinking. Definitely this simulation is not running in real time, so you can see some differences, but square waveform is perfect, and this was the thing that we were intending for. So thank you guys. In the next video, we will see that how we can interface LCD or alphanumeric LCD with 8051 microcontroller. Till then, stay safe, stay happy. Jai Hind.